Arumugalakshmi from Sri Jaindra Saraswati Vidyalaya Matriculation High Secondary School, Singanallur.
Namaste. Today we are going to see the problems in wave optics of class 12 physics. First problem. The ratio of maximum and minimum intensities in an interference pattern is 36:1. What is the ratio of the amplitudes of the two interfering waves? So the given data is I max by I minimum is 36 divided by 1. We are supposed to find A1 by A2. That is the ratio of A1 is to A2 we have to find. So we start the solution with the formula I max by I minimum is equal to A1 plus A2 the whole square divided by A1 minus A2 the whole square. Now in the LHS we substitute the I max divided by I minimum value which is given in the data as 36 by 1. So 36 by 1 is equal to A1 plus A2 the whole square divided by A1 minus A2 the whole square. Now we have to take square root on both the sides. If you take square root, it becomes 6 is equal to A1 plus A2 divided by A1 minus A2. Now A1 minus A2 in the RHS take to the LHS. So the equation becomes 6 into A1 minus A2 is equal to A1 plus A2. Now multiply the 6 inside the bracket. So we get 6 into A1 minus 6 into A2 is equal to A1 plus A2. Now segregate A1 on one side and A2 on the other side. Hence the equation becomes 6A1 minus A1 is equal to 6A2 plus A2. Hence simplifying 5A1 is equal to 7A2. We are supposed to find the ratio of A1 divided by A2. Hence, A1 by A2 is equal to 7 by 5. So, the ratio of the amplitudes are 7:5. The second problem. In Young's double slit experiment, 62 fringes are seen on a screen for a sodium light of wavelength 5893 Armstrong. If violet light of wavelength 4359 Armstrong is used in the place of a sodium light, how many fringes will be seen? So we will start the solution with the given data. Lambda 1 is equal to 5893 Armstrong and lambda 2 is 4359 Armstrong. We are supposed to find the number of fringes. We start the solution with the formula y1 is equal to n1 into beta 1, y2 is equal to n2 into beta 2, where y1 is the distance at which you get the fringes for the first wavelength. Similarly, y2 is the distance at which you get the fringes for the second wavelength. The distance at which you get the images will be the same. y1 will be equal to y2 only. Hence, equating the expression you get n1 into beta 1 is equal to n2 into beta 2. Now, we know that beta is the bandwidth. The bandwidth expression is lambda capital D by small d. Now, substituting that in this formula you get n1 lambda 1 capital D by small d is equal to n2 lambda 2 into capital D by small d. The capital D value where capital D is the distance between the screen and the slit and small d the distance between the slits are the same. Hence you can cancel the capital D and small d on the equation both the sides. Hence the equation of n2 will be n1 lambda 1 divided by lambda 2. Substituting the n1 lambda 1 lambda 2 values from the given data, we get n2 is equal to 62 into 5893 divided by 4359, which is nothing but 84. Hence the answer is 84 fringes. Third problem. A light of wavelength 600 nanometer falls on a pair of slits producing interference pattern on a screen in which the bright fringes are separated by 7.2 mm. What must be the wavelength of another light which produces bright fringes separated by 8.1 mm with the same apparatus? So the given data are beta 1, that is bandwidth, is equal to 7.2 millimeter, and beta 2 is 8.1 millimeter, and lambda 1 is 600 nanometer. We are supposed to find the lambda 2. We know the formula as lambda 2 is equal to lambda 1 beta 2 divided by beta 1. Substituting the given values lambda 1, beta 2, beta 1, we get lambda 2 as 600 into 8.1 divided by 7.2. Hence, it is equal to 675 nanometer. So, the answer is the wavelength of the another light is 675 nanometer. Fourth problem. A beam of light of wavelength 600 nanometer from a distant source falls on a single slit of 1 millimeter wide, and the resulting diffraction pattern is observed on a screen 2 meter away. What is the distance between the first dark fringes on either side of the central bright fringe? So the given data is lambda as 600 nanometer, capital D as 2 meter, small d as 1 millimeter, which is equal to 1 into 10 power minus 3 meter. We are supposed to find the distance 2y. We know the formula 2y is equal to 2 into lambda capital D by small d. Substituting the lambda value, capital D value and small d value, we get 2y is equal to 2 into 600 into 10 power minus 9 into 2 divided by 1 into 10 power minus 3. Simplifying, we get 2400 into 10 power minus 9 into 10 power 3, which is nothing but 2400 into 10 power minus 3, which is nothing but 2.4 into 10 power minus 3 meter, or it can be written as 2.4 millimeter. So the answer is 2y is equal to 2.4 millimeter. Fifth problem. A light of wavelength 5000 Armstrong produces diffraction pattern on the single slit of width 2.5 mm. What is the maximum order of diffraction possible? So the given data is lambda is 5000 Armstrong, small d is 2.5 micrometer, which is nothing but 2.5 into 10 power minus 6 meter. We are supposed to find the order of diffraction, which is nothing but capital N. So the solution stands with the formula d sin theta is equal to n capital N small n lambda. For the maximum value, you will have sin theta is equal to 1 and n small n also as 1. Hence the equation becomes d is equal to n lambda. Hence capital N is equal to d by lambda. D value and lambda value are given in the data as 2.5 into 10 power minus 6 and 5000 Armstrong. So substituting in this equation, you get 2.5 into 10 power minus 6 the whole divided by 5000 into 10 power minus 10. Hence you get the answer as 25 into 10 power minus 7 divided by 5 into 10 power minus 7, which is nothing but 5. Hence, the maximum order of diffraction is 5. Sixth problem. If I0 is the intensity of the light existing between two cross polarids kept with their axes perpendicular to each other, a third polaroid is introduced between them, what must be the angle between the axis of first and the newly introduced polaroid to get the maximum light from the whole arrangement? We know that intensity is directly proportional to the square of the amplitude. Here amplitude is given by A by root 2 into cos theta sin theta. Hence I is proportional to A by root 2 into cos theta sin theta square. A by root 2 is a constant. Hence we write this equation as I is proportional to constant into cos theta into sin theta the whole square. Now multiply and divide the above equation RHS by 4. So you get I is proportional to constant divided by 4 into cos theta and sin theta. That 4 when you take inside the square, it becomes 2 cos theta sin theta the whole square. So the equation becomes I is proportional to 1 by 4 into 2 cos theta sin theta the whole square. 2 cos theta sin theta can be written as sin 2 theta. Now the expression for intensity is I is proportional to 1 by 4 sin 2 theta the whole square. This is the expression for maximum intensity. This intensity will be maximum when sin 2 theta is maximum. The maximum value of sin 2 theta is 1. Hence 2 theta will be equal to sine inverse of 1, which is nothing but 90 degree. So 2 theta is equal to 90 degree. Then theta will be equal to 90 divided by 2, which is nothing but 45 degree. Hence the angle between the Polaroids is 45 degrees. The seventh problem. An unpolarized light of intensity 32 Weber per meter square passes through three Polaroids such that the axes of the first and the last Polaroids are 90 degree. What is the angle between the axis of first and the middle Polaroids so that the emerging light has an intensity of only 3 Weber per meter square? So the given data is I naught is equal to 32 Weber per meter square. I is equal to 3 Weber per meter square. We are supposed to find the angle theta at which it is oriented. So we start the solution with the formula intensity is directly proportional to amplitude square. Like the previous sum, the expression for amplitude is A divided by root 2 into cos theta sin theta. This is the amplitude of the light which is emerging from the second Polaroid. Hence I is equal to k into a square divided by 2 cos theta sin theta the whole square. Here k into a square is taken as I naught. Hence the equation becomes I is equal to I naught divided by 2 into cos square theta into sin square theta. Here once again the RHS we multiply and divide by 4. Hence we get I is equal to I naught divided by 2 into 4 into the 4 in the numerator we are taking inside the square. Hence it becomes 2 cos theta sin theta the whole square. 2 sin theta cos theta the whole square is written as sin 2 theta the whole square. Hence I is equal to I naught divided by 8 into sin 2 theta the whole square. Hence sin 2 theta the whole square is equal to 3 into 8 divided by 32, which is nothing but 3 by 4. Hence sin 2 theta the whole square is equal to 3 by 4. We take square root on both sides. Hence sin 2 theta is equal to root 3 by 2. When sin 2 theta is equal to root 3 by 2, 2 theta will be equal to sin inverse of root 3 by 2, which is nothing but 60 degree. So 2 theta is equal to 60 degree. Theta will be equal to 30 degree. So the angle between the axes is 30 degrees. Now the eighth problem. The reflected light is found to be plane polarized when an unpolarized light falls on a denser medium at 60 degree with the normal. Find the angle of refraction and the critical angle of incidence for total internal reflection in the denser to rarer medium. So angle I is given as 60 degree, angle R we have to find and the critical angle also we have to find. We know that the angle between the reflection incidence is totally equal to 180 degree, that is 60 plus 90 degree plus R is equal to 180 degree. Hence 90 plus 60 is 150, which you take it to the RHS, it becomes R is equal to 180 minus 150, which is equal to 30 degree. So now we have found the value of angle of reflection as 30 degree. We know the incidence, angle of incidence is 60 degree. So you can easily find the refractive index. Mu is equal to sin I by sin R. We know the formula of refraction as mu is equal to sin I by sin r, which is equal to sin 60 degree divided by sin 30 degree. Sin 60 is root 3 by 2, sin 30 is 1 by 2. Substituting the value, you get mu is equal to root 3. We know the critical angle formula as mu is equal to 1 by sin c. So sin c, you take it to the RHS, it becomes root 3 is equal to 1 by sin c. When you take sin c to the LHS, it becomes sin c is equal to 1 by root 3. So c will be equal to sin inverse of 1 by root 3. Sin inverse of 1 by root 3 is nothing but 35.15 degrees. So the angle of critical angle is equal to 35.15 degrees and the angle of reflection is found to be 30 degrees. The ninth problem. A compound microscope has a magnifying power of 100 when the image is formed at infinity. The objective has a focal length of 0.5 cm and the tube length as 6.5 cm. What is the focal length of the eyepiece? So we start the problem with the expression for L as L is the sum of V0 plus UE. Hence, here UE is nothing but the focus FE. FE means it is the focus of the eyepiece. VO means it is the image distance of the objectives. Hence, L is a sum of V0 plus FE. So, from this equation, you get the expression for V0 as V0 is equal to L minus FE. This you keep it as equation 2. Then we use our mirror equation. 1 by V0 minus 1 by U0 is equal to 1 by F. This is for the objective. Here U0 is equal to minus U0 using sign convention. Hence, we rearrange the above equation as 1 by V0 plus 1 by U0 is equal to 1 by F. In this equation, we multiply throughout the above equation by V0. Hence, we get the equation as V0 by V0 plus V0 by U0 is equal to V0 by F. Simplifying, we get 1 plus V0 by U0 is equal to V0 by F. Hence, V0 by U0 is equal to V0 by F minus 1. Hence, V0 by U0 is equal to V0 by F0 divided by F0. This equation you keep it as 1. Now, we know the formula of magnification as magnification of objective is given by V0 by U0 into D by Fe. In this equation, we use our equation 1, which is V0 by U0 is equal to V0 by F0 divided by F0. So, substituting, we get M is equal to V0 minus F0 divided by F0 into D divided by Fe. Now, in this equation, instead of V0, we use our second equation, which is V0 is equal to L minus Fe. Hence, we get the expression for magnification as M is equal to L minus Fe minus F0, the whole divided by F0 into D minus Fe. Now, in the above equation, we use our given data. The given data are magnification is 100, FO, that is the focal length of the objective is 0.5, L value is 6.5 and FE alone we have supposed to find. So, other than FE, all other expression you substitute the given data. We get 100 is equal to 6.5 minus FE minus 0.5 the whole divided by 0.5 into 25 divided by Fe. So, rearranging this equation, we get 100 into 0.5 the whole divided by 25 is equal to 6 minus Fe divided by Fe. Now, we get 100 into 0.5 divided by 25 is nothing but 2, which is equal to 6 minus Fe divided by Fe. Now, Fe, which is in the denominator in RHS, we take it to the LHS. Hence, it becomes 2 Fe is equal to 6 minus Fe. Now Fe you bring it to the one side. Hence it becomes 2Fe plus Fe is equal to 6. Hence 2Fe plus Fe is 3Fe. 3Fe is equal to 6. Hence Fe is equal to 6 divided by 3, which is nothing but 2 centimeter. That is, the focal length of eyepiece is 2 centimeter.